Alright, so today we're going to look at using something called scientific notation. So scientific notation is a way of writing really big or really small numbers in a more compact or succinct way. It definitely has lots of applications if you're working in things like chemistry, physics, engineering. We use scientific notation all the time, and specifically you'll use it all the time in your sciences in high school. So, scientific notation has the form where we're taking a number a times 10 with an exponent of n. So, the n has to be an integer, so the exponent on 10 is an integer, and the value for a has to be something that is between 1 and 10. Now it's fine if it equals 1. It's not good if it equals 10. It's not good if it equals 10 because if a is something that's 10 or bigger, it means we actually haven't simplified our number enough. There's more that we could do to simplify it. Okay. Alright, so that's the form we're going to be looking at. Now I'm going to give you a couple examples and show you kind of how we're getting a number into that form. Okay, so the first one we're going to look at is writing the number 31,500 in scientific notation. Now I know that this number is not that big and doesn't necessarily need scientific notation, but for example purposes it works quite nicely. Okay, so our first goal, remember we said that a had to be somewhere between 1 and 10. Okay, so right now this number as it stands is 31,500. That is much bigger than 10. Okay, so if you think about the decimal here, what I'm going to do is I'm going to move this decimal point and I'm going to move it over 1, 2, 3, 4 spaces so that it goes in between the 3 and the 1. So if I put the decimal point in between the 3 and the 1, now I have 3.1500. Now hopefully you remember when you're writing a decimal, those extra zeros on the end don't actually do anything. So we're going to get rid of those. And that's how we simplify these numbers so we're not writing as many digits, especially when we get to something with, like 27 digits or something like that. So I've got 3.15. But this doesn't work because now this is a totally different number than what I had. Okay, so this is supposed to be 31,500. So that 3, this is in the 10,000s position. So I would still need to write times 10,000. Okay, so it's 3.15 times 10,000. And now I still have something that is an equal value because I want to still represent the same number, just in a different way. Now another way of writing 10,000 is I can split 10,000 apart. Right? So if I split 10,000 apart, and I'm going to do it in factors of 10, because we said that our other number should be a 10 with some integer exponent. So instead of writing 10,000, I'm going to break that into 10 times 10 times 10 times 10. And another way of writing 10 times 10 times 10 times 10 is to write it as 10 with an exponent of 4. Okay, so 3.15 times 10 to an exponent of 4 is the same representation of 31,500, but it's just given in scientific notation. Okay, so some things to notice here. The exponent of 4 tells me exactly how many digits are after the 3. Right, so I had 31,500. If I look at that 3, there are 4 digits to the right hand side, meaning there are 4 decimal places to the, or sorry, not 4 decimal places, but there are 4 spots for digits to the right hand side. Okay, that tells me that the 3 is in the 10,000ths position, right? A 1 followed by the 4 zeros, so the 3 is followed by 4 digits. Okay. All right, let's do a couple really quick ones then. So here we've got this chart, so we'll fill it in. So standard form would be the number before we've done anything to it. Okay, expanded form is where we're showing it, where we're multiplying by all of the tens, and then our scientific notation in the end. Okay, so if I have the number 4,100,000, so I would need to move the decimal point in between the 4 and the 1 to make it 4.1. And then because I'm multiplying by a million to get that, the 4 was in the millions position, so there are 6 digits to the right hand side of the 4, so it needs to be followed by 6 tens in the expanded form. Okay, I got 5, so 6. So in scientific notation, we've got the 4.1 times 10 with an exponent of 6. Okay. All right, let's look at the next one. So we got 2.35 times, and if you count them all up there, there are 8 tens. So in scientific notation, that's the 2.35 times the 10 with an exponent of 8. Okay, and when I go to write that out in standard form, I'm going to start with the 2. Okay, oh my goodness. I'm going to start with the 2, and then I'm going to have the 3 and the 5, and I need to fill out the rest of my positions here. So since the exponent on the scientific notation was an 8, that means after the 2, I need to have 8 digits. The 3 and the 5 take up 2 of my 8 digits, so that means I need to have 6 more digits following after. And the reason we didn't write out what those digits were was because they were zeros. So in our expanded form, we didn't write those extra zeros. So now when you look at this number here, we've got 1, 2, 3, 4, 5, 6, 7, 8 digits on the right-hand side of the 2. Okay, so that means now our 2 is in the 100 millions position. Okay. All right, the last one here. So we've got 9.01 times 10 to an exponent of 3. So we're going to start out, we've got our 9.01 times 10 to an exponent of 3. So that would mean we need to have 3 tens coming after it. Okay. And then when I write it out in standard form, I need to have the 9, and then I need 3 digits following the 9 on the right-hand side. The 3 digits following the 9 have to be the 0 and then the 1, and then my third digit would be another 0. Okay. Now, I didn't get rid of the 0 in between the 9 and the 1, because the 1 is in the tens position. So in order for me to, it has to be maintained in the position that it was in. So we're not just getting rid of any 0 that we see. We are getting rid of the extra zeros that once the decimal point has been introduced, don't give us any new value, or don't give us any new information. Okay. All right. Let's look at one where we're taking a small number and writing it in scientific notation. So those ones were big values that we made a little bit more compact. What about the small numbers? Okay. So with this one, we're going to do the same kind of thing. So again, we want to get it in the form of a times 10 to an exponent of n. And remember, a has to be somewhere between 1 and 10. So I'm going to move this decimal point over to where the 5 is. So I'm going to move it 1, 2, 3, 4 spaces so that it's going to go in between the 5 and the 4. So now I have 5.4. Okay. But 5.4 is not the same value as what I had before. So if you look where that 5 was, that 5 was sitting in the 10,000ths position. So in order for this number to still be 54 10,000ths, what I need to do is 54 100,000ths, where the 5 is in the 10,000ths position. What I need to do is I need to divide this by 10,000. Okay? Now, I don't want to write that as divided by 10,000 because I need to know the exponent on the 10. So I'm going to rewrite the 10,000 as 10 times 10 times 10 times 10, right? Because there are 4 tens in 10,000. So now I have 5.4 over top of 10 to an exponent of 4. But that doesn't help me. I need to move that 10 up to the numerator. But if I move it from the denominator up into the numerator, the exponent is going to change from being positive to being negative, right? And we kind of talked about that in our last lesson. A negative exponent means move it to its opposite spot and change it from being negative to positive. Well, it works the other way. If I move something that has a positive exponent in the denominator and I move it up to the numerator, the exponent goes from being positive to being negative. So now I have 5.4 times 10 with an exponent of negative 4. Okay, let's fill in another chart really quick so we can get some quick examples here. So 0.00091, or in this case that's 91 91 hundred thousandths. Okay, so I would need to move the decimal 1, 2, 3, 4 spaces again. So I've got 9.1. Okay, now I moved it 4 spaces, so that means I had to move it by 4 powers of 10. Okay, another thing to notice is that with this one, I have 4 zeros in front of the 9. So that means there are going to be 4 tens in my denominator. Okay, so in scientific notation, this becomes 9.1 times 10 to an exponent of -4. So when we're looking at the negative one, it tells you how many zeros should be in front of that first digit. Okay. All right, the next one here, I've got 5 divided by, and if you count them up, there are 8 tens there, so that would be 5 times 10 to an exponent of -8. And when I write that out, I know I need to have a 5, but then in front of the 5, there need to be 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and then the decimal point is going to go in between those first 2 zeros. Okay, so when you're working with scientific notation of small numbers, the exponent tells you how many zeros are sitting in front of that digit. Okay, then we've got, in this last one here, we've got a 1.3 over top of, and then it was times 10 to an exponent of -3, so there's going to be 3 tens in the denominator here. And so I'm going to have my 1 and my 3, and then there should be 3 zeros in front of the 1, and we put the decimal point in between the first 2. Okay. Now, scientific notation is nice because it allows us to multiply really big numbers without having to use our calculators. So if I was to try to type this into my calculator does not have enough digits to show this to me. Okay. So what I can do here, if I've got 3.6 times 10 exponent 9 times 2.5 times 10 to the exponent of 7, I can move my coefficients, my a's, so that they are next to one another, and then I can have my powers of 10 next to one another, because if all I'm doing is multiplying, multiplication is commutative, so I'm allowed to multiply in whatever order I like. So if I was to look at these two guys here first, 3.6 times 2.5, 3.6 times 2.5 ends up giving me 9. So I have 9, and then 10 exponent 9 times 10 exponent 7, I would add those exponents together to get 10 with an exponent of 16. Okay, now that's a number that my calculator is not going to show me, but it's probably going to give me that answer in scientific notation. And it's going to look a little bit different on each of your calculators. If you have questions with how yours is showing it to me, feel free to email. Let's do some division too. We can divide really small numbers as well that we otherwise wouldn't be able to type in. Okay, so same idea. I'm allowed to multiply and divide in whatever order I like because it's commutative. I just have to make sure that everything's included. So if I was to look at this part first, I'm going to look at the 4 divided by 8. Okay, 4 divided by 8 is going to give me 0.5. So I'm going to leave that for now. Then I've got 10 exponent -20 divided by 10 with an exponent of -15. Now if I was to use my exponent laws here, because I'm dividing, I'm going to subtract these two exponents. And when I subtract those two exponents, it's -20 minus -15. And -20 minus -15 is the same thing as -5. Okay, so now I've got times 10 to an exponent of -5. So that would mean in front of this 0, I would need to have 5 zeros. But this is a problem because this right now is not the form for scientific notation. We've said that the form for scientific notation, A has to be between 1 and 10. And right now it is not between 1 and 10. It is smaller than 1. Okay, so if you think of what this means that I'm putting 5 zeros in front of this 0. Well, that means I just didn't move my decimal place far enough, because there's still an extra 0. The decimal point still needs to move one more spot over so that the 5 is actually in front. So since I already started with 5 zeros in front and there was still an extra one to go, I'm going to write this as 5 times 10 with an exponent of -6. Okay, so you can do this division and multiplication without using your calculator, and you can use scientific notation to make it simpler. Just double check that once you've done your multiplication or your division, that A is actually between the two values that it's supposed to be, and if it's not, then your decimal point still needs to move a little bit more, and so that's just going to change your final answer a little bit. Okay, all right, there's your scientific notation rundown.